Welcome back to Academic Avengers. Today, we're diving into the fascinating world of the smallest building blocks of the universe, atoms and their structure. Imagine this. Everything you see, from the stars in the sky to your own body, is made up of tiny particles called atoms. These particles are so incredibly small that even the most powerful microscopes cannot make them visible. Atoms are not all the same. There are 92 naturally occurring types of atoms, and scientists have created even more in laboratories. Each atom belongs to a specific element, a substance that cannot be broken down into simpler substances. Examples of elements include hydrogen, carbon, and lead. Atoms vary in size and mass, depending on the number of protons and neutrons in their nucleus. The mass of an atom is determined by these particles in its core. For example, a hydrogen atom is the lightest atom, as it has only one proton and no neutrons in its nucleus. A carbon atom is 12 times heavier than a hydrogen atom. A lead atom is 207 times heavier than a hydrogen atom, making it one of the heaviest naturally occurring atoms. This difference in size and weight is what distinguishes one element from another and determines its unique properties. Atoms are not indivisible. They consist of even smaller particles called protons, neutrons, and electrons. These subatomic particles define the characteristics of an atom. Protons are positively charged particles found in the nucleus. Their positive charge attracts the negatively charged electrons, keeping them close to the nucleus. Neutrons are neutral particles that also reside in the nucleus. They contribute to the mass of the atom and weigh slightly more than protons. Electrons are negatively charged particles that orbit the nucleus. Their mass is negligible compared to protons and neutrons, but their charge balances the positive charge of the protons, making the atom electrically neutral. The nucleus, where protons and neutrons are tightly bound, is tiny but contains almost the entire mass of the atom. Surrounding the nucleus are the electron shells, where electrons move in specific orbits. Each shell has a fixed capacity for electrons, and new shells form as older ones fill up. For example, a carbon atom always has 6 protons and 6 electrons. Most carbon atoms also have 6 neutrons, creating a stable nucleus. Atoms of the same element can have different numbers of neutrons, resulting in isotopes. These isotopes have the same chemical properties because their number of protons and electrons remains unchanged, but their masses vary due to the differing neutron counts. Take hydrogen as an example. The most common hydrogen isotope has no neutrons in its nucleus. Deuterium, an isotope of hydrogen, has 1 neutron and is twice as heavy as the main hydrogen isotope. Tritium, another hydrogen isotope, has 2 neutrons and weighs 3 times as much as regular hydrogen. An exciting application of isotopes is radiocarbon dating. Scientists use the radioactive isotope C14 to determine the age of organic materials, like wood or fabric. For example, ancient objects such as the wrappings of a mummy can be dated by measuring the remaining amount of C14. Over time, this isotope decays at a steady rate, and the leftover quantity allows researchers to calculate the object's age accurately. Inside an atom, 3 primary forces govern its behavior and stability. The strong nuclear force is the most powerful force in the universe. It binds protons and neutrons together in the nucleus, overcoming the natural repulsion between positively charged protons. However, it only works over extremely short distances. The electromagnetic force holds the electrons in orbit around the nucleus by the attraction between the positively charged protons and negatively charged electrons. This force also plays a role in light and electricity. The weak nuclear force causes radioactive decay. This force allows particles to be ejected from the nucleus, which is a crucial process in nuclear reactions and changes in atomic structure. The electromagnetic force extends beyond the atom, affecting interactions between atoms, while the strong and weak forces act only within the nucleus itself. Atoms are incredibly small, but essential to understanding the universe. Their unique structures, subatomic particles, isotopes, and the forces within them determine the properties of elements and the matter they compose. By studying atoms, we unlock the secrets of everything from the smallest particles to the vastness of the cosmos. Thanks for watching. Check back every week for new videos, and don't forget to like, subscribe, and comment down below.